Well, hello. Welcome to AP Chemistry, summer work. And what I'd like to do today is just give you sort of an introductory uh, lesson, if you will, on some things that you probably already know. Very easy. I just want to get you familiarized with some units that you're going to need in this class and in any future science classes you take. So, chemistry is a science of observation. And those observations can be qualitative. For example, qualitative meaning it's a quality of something. I could notice a change. For example, if I'm doing an experiment and something turns from colorless and clear to pink, well, we could see that a chemical change has occurred. If we take a beaker of some blue copper solution and we put something in it, I would put a little piece of zinc in there, you're going to see the zinc start turning brown and the copper losing its solution, losing its blueness because a chemical reaction is taking place. So those are qualitative measurements. Do things heat up or cool down? Uh, that's qualitative. We can feel the beaker if it warms up. Quantitative, though, is as if we actually measure the temperature change. Then we can actually have a quantity to attach to that. Or another quantitative measurement would be how many grams of a chemical compound am I going to make? So what we're going to need to do is make sure that you understand the units for the important quantities that we look at in chemistry. Let's see if I can just switch the old camera around here. Still using my laptop camera. Now, measurement, we use what's called the international system, the SI system, and furthermore, to build additional units that we need, other than units that discuss mass, length, time, temperature, current, and amount of substance, we combine units, and it's always based on what's called the MKS system of units. MKS, M stands for meter, K stands for kilogram, and S stands for second. So we make other units out of that. I'll show you that in just a moment. But let's take a look at units that we have for things like mass. Mass, are our base unit in the international system, is the kilogram, abbreviated kg. Okay, kilo means 1,000, so a kilogram is 1,000 grams. Length, the unit that we use, is the meter. The meter is a little bit larger than a yard, so you kind of have a frame of reference. But of course, you've been hopefully using meter sticks since elementary school. Time, we use the second, and the abbreviation is S, not SEC. We don't say second and abbreviate it that way. We just use an S. Okay. Temperature. Now, temperature, you might be thinking, well, it's obvious. We use Celsius. Yes, we do, but we also have another unit called Kelvin. That's a capital K. And Kelvin is your degrees C plus 273.15. And what this relationship is, why we have to take our degree C and add 273.15, has to do with the concept of absolute zero. And that's something that we're going to learn about, spend a little bit of time on. So moving along, the electric current, should we be lucky enough to get to electrochemistry, which I think we can do. Electric current, the unit is ampere, abbreviated capital A. And amount of substance, the amount of substance, you might think, well, isn't that just mass? Well, mass is one way to express the amount of material we have. But when we start talking in the world of chemistry, we have a unit called the mole, M-O-L-E, and it's abbreviated M-O-L. Saves you a lot of ink. It's also given the symbol lowercase n. So these are fundamental units: mass, length, time, temperature, electric current, and amount of substance, kilogram, meter, second, Kelvin, ampere, and mole. Now, what do I mean by building other units? Well, let's take a look at for example, a unit of volume. See if I can switch the old camera here. So volume is a derived unit. Volume is, well, think of a volume of a cube. Length times width times height. So if I'm talking about meters, well, it's going to be length times width times height if I'm using all meters. So the volume of something in our system would be cubic meters, or meters cubed. So we write it like that. Meters to the third power, meters cubed, and that's a volume unit. You may also be familiar in the so-called metric system with something called the liter. The liter is smaller than a cubic meter. As a matter of fact, there are 1,000 1,000 liters in 1 cubic meter. Okay, and I would encourage you to try to prove that to yourself. It's a good exercise to show this relationship. Let me see some other things. Well, volume is going to be length squared. Or sorry, length cubed. Area would be length squared. But let's take a look at other types of units that we might see. We might see force units. Force. Now, a force is typically something like a push or a pull. Okay, that's what we mean when we talk about force in physics. And force has a very different unit, but it's built from these. Force, if you think about Newton's second law, force is equal to mass times acceleration. Okay, this is a very famous equation in physics. So let's see what kind of unit force works out to be. Well, mass is going to be kilograms. Well, kilogram is one of our fundamental units. And acceleration. Acceleration, let me get rid of some of this stuff here. We don't need all this right now. Acceleration is a change in your velocity, or your speed, if you will, over time. So let's say, for example, you're driving along at a certain velocity, and that would be just meters per second, because velocity, or speed if you want to think about speed, velocity is a little different. But if I'm driving at 25 meters per second, that means every second my position changes by 25 meters. Okay, so it's very straightforward. But if I'm stepping on a gas pedal, for those of you learning to drive, if I'm stepping on a gas pedal, you know that you are starting from zero. If you're pulling away from a stop sign, hopefully you're starting at zero, and you step on, and your speed increases with time. So you go from 0 meters per second to 12 meters per second to 15, 20, and 25. So acceleration is the change, how many meters per second okay? In other words, my speed, meters per second, is increasing or decreasing per unit time. So we have units of, first of all, I should write it as the change in the speed and the velocity and the change of time. That's acceleration. And that has units of meters per second squared. Meters per second squared. So meters per second squared, if I put it back up into my force equation, the units are going to be kilogram meter per second squared. Okay? So the problem with that is, who wants to keep writing that? Because it's like a whole bunch of different things, kilogram, meters, and second squared. So we give it a new name, and we define it as something called the Newton, named after, of course, the cookie Fig Newton, named after Isaac Newton, right? So there's a unit built from other units. Another one would be pressure. The pressure of something is force, I don't know why I'm writing an A force per unit area. That's why I was writing an A. Force over unit area. We just learned that would be a Newton for my force, and area is length squared. So Newton per square meter. And again, we don't want to write that, so we come up with a brand new symbol for this unit, a new name for this unit, and it's called a Pascal, abbreviated PA. So as we go through chemistry, you're going to, got my hands all messy from this meter stick. We're going to be learning about these other units. Now, let's just take a minute and talk about metric prefixes that enable us to make more usable units for us in chemistry out of these base units. Take, for example, the kilogram. Right? We very seldom, as a matter of fact, we never go into the lab and measure out 2 kilograms of something. You do that if you're baking bread, probably, but not when you're in a little chemistry lab. So what's a better unit for us? Well, the better unit for us would be grams, just G for grams. Now, what is the relationship between kilograms and grams? Well, kilo, that prefix, means 10 to the third, or 1,000. So 1 kilogram is equal to 1,000 grams. So it's important that if you have to convert back and forth from kilograms to grams or grams to kilograms, you know what you have to do. We set up, as a matter of fact, something called a conversion factor. I could write it as this: 1 kilogram is over 1,000 grams. Since these two things are equal to each other, we can come up with an identity here and use this to solve problems. Likewise, we can say, well, 1,000 grams is 1 kilogram. So these two quantities are exactly equal to each other, although mathematically this comes out as 1/1,000 and this comes out as 1,000. So let's take a look and see how we can use this. Let's say I've got 555 grams and I want to know how many kilograms I have. Well, what we would say is, all right, 555 grams, I can multiply this by a conversion factor. 1 kilogram is 1,000 grams. And so when we do that, this is just like multiplying by a fraction. The way I write this with this little t, and I can keep going if I want to, it's like setting up almost like a little spreadsheet or something, but it helps you keep things in order, in line. But if you prefer, you can write it like this: 555 grams times 1 kilogram over 1,000 grams. For me, using this sort of a method where we divide things up keeps things in order a little bit better. But this is a simple calculation. You don't need a calculator for it. It would just be 0.555 kilograms by 10 100,000, and you're good to go. So, a simple example about using a conversion factor. I'm going to refer you to a couple of online tools. One is a review of scientific notation, and I'll post a link for that. And the other is some reading in an online textbook. That'll be your first assignment, and it's just background material, very easy to read. As a matter of fact, the text that I would like to stick with, we have an in-class textbook that we can use for problems and stuff, but there's an online platform called OpenStax. I happen to have purchased the hard copy of the book, but every single thing that's in the book, and it's actually a 2-volume set, everything that's in here is online, so I'm going to post some links to that as well. So I hope you enjoy this, and I hope you really enjoy the summer work. We always have a lot of fun. The AP class, we always take it a couple notches above, and we have a good time. So anyway, that's all I have to say. And welcome to the summer work, and welcome to my class. Take care.